In the next few videos, we're going to be talking about vector multiplication. There are 4 different types that we're going to consider. 2 of them are going to be used more often, and then 2 are going to be used more sort of just as shortcuts to help us cut down on our work we need to do. One important thing to note is depending on which type of vector multiplication we're doing, we can have a result that's either a scalar value or a vector value. So that's very important to keep in mind whether we're dealing with a scalar or a vector. So let's go ahead in this video and talk about our first type of vector multiplication, which is something that hopefully you're familiar with, and is called the dot product. And you might also hear this referred to as the scalar product. As we're going to see, the result is a scalar, so it falls into this category here. So let me just go ahead and write our important equations. So we would write this if we have 2 vectors, a and b, as a, our vector a, dot b. And so you might recognize this notation from some of our Maxwell's equations. So we would say a dot b is equal to the magnitude of a times the magnitude of b times cosine of the theta between a and b. And so it's important to note that this angle theta AB is the smaller of the 2 angles between a and b. So AB is the smaller of the 2 angles. And I'll draw what this looks like here in a second graphically. Between our 2 vectors, A and B, when drawn tail to tail. And so of course they're not always going to be right next to each other, but if they're drawn tail to tail, let's say we have a vector A that looks like this, and a vector B that looks like this, for instance. So of course there's 2 angles that we could sort of associate with this. So let me switch colors here. So of course we have this angle here, and we have an angle that is going here. And so what we're saying is that because we're looking at the smaller angle, the smaller of the 2 angles, that the theta AB would be this one indicated by the red arc. Okay, so we can also express a relationship for these things in Cartesian coordinates. So let's specify a little further and say that our vector A is equal to some x component, some y component, some z component, and our vector B we can define similarly as some x component bx, some y component by, and some z component b sub z with angled brackets because these are vectors. So if that's the case, then what we can say is that a dot b, so these are both vectors, is also equal to ax times bx plus ay times by plus az times bz. So basically we're just multiplying the components that are in sort of the common place and then summing all of those products. So what we can do is we can sort of use these 2 equations together to figure out certain angles or certain components depending on what information we have and what information we want. So one thing to point out again is that our product is a scalar. So here we have magnitude, magnitude, and this is a scalar value. And if we look at this second equation, of course we have scalar values, scalar value, scalar value, all being added together for one single scalar value. So with our dot product, we get a scalar result. So a few more things to talk about with regards to our dot product. We can use this to help tell if 2 vectors are orthogonal. And so orthogonal is just another way of saying perpendicular. Perpendicular. So orthogonal or perpendicular. And oftentimes I'll just abbreviate, well not necessarily abbreviate, but I'll write perpendicular by writing these 2 lines that are perpendicular to one another. So that's a symbol for perpendicular. So 2 vectors are orthogonal with each other if that dot product is 0. So if a dot b is equal to 0, then our 2 vectors are orthogonal. And of course the reason is if we have this theta sub AB here equal to 90, well of course cosine of 90 is equal to 0. So cosine of 90 degrees is equal to 0. and then we have cosine of, we have this 0 times the magnitude, so of course the dot product is ultimately 0. So let's talk about briefly some properties for our dot product. So first, our commutative property, or commutative law as I have it labeled here, and to be consistent with the notes, let me just label these as 1. So our commutative law is basically saying it doesn't matter which order we do this. So if we do A dot B, that's the same as saying B dot A. And that should be pretty evident from the two boxed equations that we talked about previously. Our second property is our distributive law. And so our distributive law is saying if we have A being dotted with some sum of vectors, so A dot B plus C, and let me make my arrow consistent there, then that's just saying that's the same as the sum of A dotted with each of those. So we can say this is equal to A dot B plus A dot C. And then finally, one thing we can note is what if we have a vector that's dot product of itself? So if we have, for instance, A dot A. Well, if we plug that into the above equation, particularly if we focus on this top one, we can see we have now A, so the two magnitudes, and then cosine of the angle between the two. Well, if it's the same thing, the angle between the two is 0, and cosine of 0 is 1, so we're just going to have A squared, where A is the magnitude. So we have magnitude of A squared, or we could just write that as A without an arrow squared. So another important thing to note, sort of based on that first equation with our cosines, is we could talk about relationships between our unit vectors in Cartesian coordinates. So if we have the dot product of any two directions, sort of that are not the same, so u of x dot u of y, or u of y dot u of z, or if we have u of z dot u of x, any of these are going to be equal to 0 because, of course, we said if we have perpendicular or orthogonal vectors, then their dot product is going to be 0. And, of course, we know that our x, y, and z unit vectors are all perpendicular to one another. And, of course, remember, we could switch the order of any of these based on our commutative law up here. Another thing we can note is that if we have the dot product of any of these unit vectors with themselves, so u of x dot u of x, or u of y dot u of y, or finally u of z dot u of z, that's just going to equal to 1 because, again, we're using sort of this third property here, but instead of having a magnitude of some arbitrary value a, because these are unit vectors, by definition their magnitude is 1, so we have 1 squared, which gives us 1. So that's all for our dot product. In our next video, we're going to take a look at our cross product, which is the other of our second commonly used one, and then we'll talk in a later video about the two different forms of multiplication which are just sort of used as shortcuts in our math.